Villavicencio.
Thank you. Thank you very much for the organizers to give me the opportunity to present this work here. It's very nice to see all these groups together. Well, this is a work in collaboration with Eduardo Fraga and Leticia Paliares, published in the end of the past year. Well, the idea of this work, of course, is to see if the anomalous magnetic moment is how it is affected by an intense magnetic field. And when you talk about extreme magnetic field, of course, we are approximated in the lowest Landau level. So it's not only a fact of an academic way to see this, because we are in magnetic field stronger, much stronger than the one we can reach in heavy ion collisions. But we're trying to see also what are the structures that appear, the form factors, you know, that are modified. There are some new elements when you include a strong magnetic field. Besides, it is easier to calculate in this approximation. When we start this work, there was only one work in this subject to calculate the effect of magnetic field in the anomalous magnetic moment, but a very slow magnetic moment. So there was no way to compare. Past week, the May 1 group published a preprint with this with the functional renormalization group formalism. So now we have something to compare with. Okay. So this talk will be just a brief introduction to the anomalous magnetic moment, like they appear in textbooks, and the triangle diagram in terms of the lambda levels description, which are the structure of the form factors when we work with the lambda levels, because the system is quantized in different levels, so it's not just as a single parameter to be identified as the anomalous magnetic moment. Okay, so okay, they follow an anomalous magnetic moment in the lowest Landau level approximation, with much more simple than calculate the full formats. And well, the result here, this is the triangle diagram, will be infrared divergent. So I will show how to regularize it in two aspects and the numerical results. So you can find in the textbooks, this is the usual description. You have the Dirac equation, you know, but if you want to calculate the quadratic Dirac equation, there's appear these terms proportional to the commutator of the covariant derivative, which is the electromagnetic tensor, you know, multiplied by the sigma mu nu, and this factor here is known as the G factor. So when you include radiative corrections, there will be corrections to this term, and these corrections are the anomalous magnetic moment corrections. So if we express this term expanded in this spin matrix, we'll see that there's a, well, this is factor 2. This B, an electric field. This is the photon, electric and magnetic field, and this is a spin projection. And this is very important to keep in mind. Here, the electric field is the Lorentz invariant computation of the magnetic moment. Okay, so it is not related with the electric dipole moment. Mm. So when we include radiated corrections, there will be some correction to the G factor, and this is what is known as the anomalous magnetic moment. Okay, so the vertex, thinking about photon. Well, this is a QED, of course, but and the title it's about quarks anomalous magnetic moment, but after all, it's the same. You just keep some overall factor and change the charges involved, and in QED the expressions are the same as QCD. Where's the point here? So here you have the vertex, the photon fermion, anti-fermion vertex, and it depends on well it's energy momentum conservation. So the p minus p prime or p prime minus p is it is q is equal to q. So we have a form factor that depends on p and p prime. So using that the system is on shell, so this is the Dirac equation, and the use of the Gordon identity, we can express everything in terms of the photon energy momentum. So after all, this is the M matrix is it has one component of one form factor that is related to the corrections of the coupling, photon fermion coupling, and here is the anomalous magnetic moment form factor. So if we go to on shell, I mean this with q square equals 0, the photon momentum, that's the anomalous magnetic moment. Okay. The vertex correction, so the magnetic one loop, you see we have one photon interchange in the case of QED, sorry, and this is the triangle diagram. So we have here the photon propagator and fermion propagator as usual, and the anomalous magnetic form factor in terms of the Feynman parameters can be written in terms of this. So if we set q square equal to 0, the mass cancels, and we arrive to the well-known result alpha over 2 pi. And the case of quarks is the same. Basically, just replace the electromagnetic coupling alpha by the alpha strong, and include this color factor. So that's what I'm saying. This the expressions are almost the same. Okay, what happens now with the anomalous magnetic moment under extreme magnetic field? For the moment, this is the general triangle diagram for the corrections to the vertex, and we include a constant uniform external magnetic field around the z direction. So first of all, the system is quantized in lambda levels, and now we well, depending of this is a Landau gauge, so we already have this direction, py direction, but it will not appear at the end of the calculations. And uh, we lose one of the momentum directions, and instead we have lambda levels. So z, xi prime are space parameters, and the T matrix, the transfer matrix, will be proportional to Dirac delta in the parallel direction. This is the polarization vector, and the correction now depends on n and n prime, the lambda level parameters. So what can be interpreted here? What is the anomalous magnetic moment? Well, it is a bit hard to say, because you have this different n prime. Maybe you have to diagonalize and maybe, well, there are some colleagues here that are working in this stuff, trying to solve this completely. So maybe in the next conference they will show the complete result. And okay, now the matrix elements. You know, A, this is the photon field. It's only momentum space. It provides you the polarization vector. But the fermion, you have to set the different values according to the lambda level. So this is explained in this is expressed with the spinors for each lambda level. Okay, this function f is actually a matrix. It's a diagonal matrix in spin spin space. So it depends on the perpendicular values of the position here and this momentum. This is the complete scenario when you have a magnetic field in general. This will be also on shell, and defined here the magnetic length for each charge. Okay, the energy will be the energy of the incoming fermion. Will be the energy perpendicular, but including but in terms of the lambda levels, also here in the outcoming fermion or anti-fermion, and the photon, of course, we consider it on shell. Okay, but what happens with the lowest lambda level? The problem simplifies a lot. Let me see something. Sorry, let me. Here you see we have a the propagators. This is in vacuum, but the propagators now, the magnetic field now becomes the local propagators times a Schwinger phase, and then there are a series of lambda levels. The gluon field remains the same. So, okay. So, well, this is the we consider only this diagram because it's the most dominant if you're thinking about QCD. The gluon dominates. So at the lowest lambda level, we can integrate first all the exponential terms that appear. So what are the exponential terms? Well, the photon Fourier transformation, the Gaussian terms that appears in the quark propagator, in the propagator expanding in lambda levels, the Schwinger phase that is here. Yeah. So so this must be integrated term by term, but it reduces to something very simple. so this term here. So now we have only one integral in momentum, in the perpendicular momentum, and this term g here is, well, this is the using the Feynman gauge. Now this is reduces on to the spinors in of the lowest Landau level, and this is the propagator only with parallel components, and the appearance of polarization projectors, no, that will appear with the lowest Landau level. And they're usually the full fermion propagator are composed with both polarizations, but the lowest Landau level has only one. So this is a most simple scenario, or looks like. So let me show you what's the structure now. So first of all, we can still do the on-shell lowest Landau level fermions, because we are dealing with the spinors of the lowest Landau level. So this is the equations of the Dirac equation in this case. So we can also provide a Gordon identity with this only with the lowest. I forget to put the parallel, but this is a parallel, you know. So for the parallel momentum in the lowest Landau level with the lowest Landau level spinors. So here it is, and sigma mu nu is the commutator of parallel gammas, gamma mu and gamma nu. So the description is seems to be more simple if we split in terms of polarizations plus or minus. So this is now the new structure that appears at the lowest Landau level. So you have a contribution to the charge, but only on the parallel direction. So the coupling of the photon with the right coupling of electromagnetic photon with quarks now will be different. The charge, this means that the charge will be different from the parallel projection than the perpendicular one. So here we have the form factor that correspond to the anomalous magnetic moment, and we can see that only it's a contribution to the parallel directions, and there's the appearance of this third term. You see that is proportional to q mu. This, if we turn back to the Lagrangian, it contributes to the divergence of the gauge field in the parallel direction. So this term usually appears in the, well, these terms correspond to the gauge fixing. So our interpretation, this is absorbed in the, if you put some gauge fixing parameter, this can be absorbed with this can be absorbed. Okay. So what's happening with the now this new anomalous magnetic moment contribution? Because if in vacuum we have the correction is 1 plus a, no, times the contraction of sigma mu nu f mu nu. So now this will be the contraction of sigma mu nu f mu nu, and this is the new contribution. So we can define something like a polarized anomalous magnetic moment from plus or minus. It's as well most simple for a description, but the corresponding anomalous magnetic moment will be the sum in principle of the plus and minus polarization. The direction here, this S, this sign. So what is this? If you spread this in the asymmetric, it corresponds to the, if you remember, there was the magnetic field and the electric component, but this has not to be confused with electric dipole moment. So this is still anomalous magnetic moment, okay? But in such a direction that electric photon is in the z direction are modified. So if we spread this in terms of the sum of the A plus and A minus and the difference, this should be so the what one can call anomalous magnetic moment. And you see it just affects the electric part, and this difference contributes to some kind of pseudo-scalar coupling. This pseudo-scalar coupling indeed is well, you know that the magnetic field can break parity, so but we don't know yet what to do. This is an electric component of the photon field. So okay, the result here is very compact, so we can deal with it. For the plus and the minus, the only difference is this function here, where the z is one of the Feynman parameters. So f plus has this form, f minus has this form, and if we want to set q squared parallel equals 0, because it depends of parallel components of the photon momentum, but this is not on shell. So if we want to set this term to 0, we have the two choices to set the z component of the incoming and outcoming momentum equal, or this approximation that's extremely high momentum pz. Oh, sorry, this is pz too. So the momentum in the z direction much higher than the quark mass. So in those cases we can set q parallel square equals 0. So we arrive to this term here. This is the anomalous magnetic moment in the vacuum, and we make a change of variables here in the integral, and we arrive to this term. So we include here a magnetic Gluon mass, a Gluon mass, because this thing is infrared divergent, but it is controlled with a Gluon mass. So what can we do with this? So we will explore two scenarios. One is more related to low energy prescriptions, more familiar, more near to, for example, Schwinger-Dyson equations. But we have some higher masses. So the Gluon mass we approaches to 0.3 GeV, and the quark mass something similar, you know. And the other one is magnetic address Gluon self-energy. So what we do here, well, there is the lowest Landau level also polarization function of gluons that was already calculated by some people here here in the audience, and so we pick this contribution as a gluon mass squared. You know, this function here depends here on the magnetic length. Everything depends on the perpendicular momentum, and this function here we can approximate it in the chiral limit as m squared over k squared as 0. So this factor is 1. And we will include two scales for the strong coupling and the quark masses. The 1 GeV, so those low energy enough, and but to treat it as a perturbation, and also square root of EB. So here are the results. First of all, let's see the case where the magnetic the gluon mass is squared is proportional to this polarization function, and so we can see that the anomalous magnetic moment is very small, but we can also move further for lower values of the magnetic field, and we can see that for the U and D quark there's a difference. It is because of the charge, but it's not much difference if we consider the scale as 1 GeV or the scale as magnetic field. Okay, and here is the anomalous magnetic moment separated in polarization directions, divided the vacuum, so we do not include the effect of the scale in the on the scale, and we can see that this is the plus and the minus are changing in sign. So the projections in the P minus is negative in the anomalous magnetic moment. We believe that this is the most physical the physical congruent description, no? But the other one has totally different behavior. You can see here the U quark and the D quark now increase, and it's a very large value, and it also varies considerably if we take a fixed scale or magnetic dependent one. So I have to say that I have to say that even if we believe, of course, well, we believe that this results, as I say, with the polarization function of as a correction of the effect of the gluon mass is the correct prescription. But however, results recently published in the past week are more near about coincides better with those results by setting a fixed gluon mass of 300 MeV and the quark mass of 350, so constituent masses. So so as a conclusion, the anomalous magnetic moment contributes completely suppressed in the lowest Landau level of the modes, and only contributes to this easy electric direction of photons. The infrared divergences are controlled with gluon mass. As I told you, the prescription of this gluon self-energy is closest to the physical description, but compared with the last week results, seems the other prescription of effective masses is coincide with this. So we need first of all, we need the full full lambda level description. So encourage colleagues are working on this to finish this work. We have to see what happens with this pseudo-scalar contribution, so that we don't know yet. Of course, we need other models to compare with. So, yeah, we're waiting. So, thanks very much.
So we have time only for one quick question, and we have discussion later.
Very quickly, it seems that your result depends on the mass of the gluon in this case.
Yes.
But if you would do this in QED, the intermediate photon would be also a massive photon.
Yes.
You could also use the same formula that you, can you show the formula there that you used? And what I wanted to comment is that that is just, so if you, for the mass that you use, the polarization tensor function, yes. The problem with that way of treating the mass is that if you really look for the dispersion relation solution, including this polarization function, your gluon or photon still is massless. So that is not a proper way to treat the mass of the gluon or the photon, by that matter. In fact, what Enrique and Jorge and Marcelo have shown is that the gluons or photons develop a mass only if you are not in a constant magnetic field, but you have fluctuations. And the mass is actually proportional to the fluctuating parameter, the width of the noise. So I'm not sure that this is the correct way to treat the infrared divergence.
More than that, I mean the mass parameter. Well, in gluons at least, this is a common way to attack this this problem. The people used to put gluon mass by hand, and it's not. And sometimes it's not enough to correct the infrared divergence. So in this case, we can, but this is if you think this is only higher corrections, you know, it's something that if you want to think is like a self energy. So you continue with the bubble diagrams and sum it geometrically, and this will be the contribution. This is the mass function we are considering. So in this sense, this is nothing. This is not put by hand. This is the logical way to include energy corrections. One particle.
I think we can leave the discussion for the discussion session. And Norberto will be the first to ask in the discussion session. Okay, so let's thank Cristian again.
Bye.
It's working. Okay.
The next speaker is Fabio Braghin. Please.
Braghin. Okay, so thank you for the organizers for this time to talk about my work. Some of you have already listened to it, but some of you did not. So to talk about these kind of derivations of effective couplings between mesons and quarks, under a magnetic field, that's the intention, I have to pass by discussing how it works in the vacuum. Otherwise, it's not really clear how it works. So this is based in some works that are published and in ongoing work with Cristian and Marcelo. I just mentioned what we are doing. This is the outline of the talk, some motivation, some example of what I intend to do with the Nambu-Ionala-Zeno model, and then discuss how we can obtain the quark model from quark interactions, and then some couplings in the under a magnetic field, weak magnetic field. So this is there's no new issues in this slide. I mean, the motivations is to try to understand if and how magnetic fields may provide observed quantities in relativistic heavy-ion collisions, and maybe to detect some hint from it in dense stars, and then to face this behavior as probe of the system, but also as a probe of the system not only under magnetic field, because if you compare to real first principles calculation, we can have a hint how it really works, the strongly interacting system. So there are different ways to face these contributions from magnetic fields in these systems. And then we can try to understand further and identify how relevant degrees of freedom operates in these systems. So, wait. So just one example of doing so, I will consider here this is a work done with a former student. We picked up the Nambu-Ionala-Zeno model without further interactions, where, just to remind, this coupling constant, it comes from quark-anti-quark interactions, so it is flavorless, and it has some deep meaning that can be traced back to gluon dynamics. So, the effect, how the Nambu-Ionala-Zeno works under a magnetic field has been considered in a lot of works. Many people are here in this conference, and so the idea is to try to understand how this coupling constant might behavior under a magnetic field. So for this, I will consider one loop corrections to this coupling constant by the model itself. So this will be a sort of polarization contributions where one magnetic field insertion can be taken into account. So this brings the idea of quark-anti-quark interactions by means of a gluon cloud that we'll discuss later in this talk, and then that can be associated to higher order corrections to the coupling constant between a quark and an anti-quark. So this, besides the one gluon exchange that usually associated to the model, we can go further and take two gluon exchanges and maybe further. And then by applying this one loop background field method to this model, we have a corrections. I will not show the equations, the derivation, but we have a Lagrangian correction. So this is effective, potential effective action for the Nambu-Ionala-Zeno. So we have a correction for the quark mass. This is precisely the contribution that comes from the gap equation. This is a condensate contribution for the quark mass that's flavor dependent. And then if you go to the higher next order, we have quark anti-quark corrections, in which now the coupling these corrections to the coupling constant will depend not only on the magnetic field, but they will be dependent on flavor. So they break chiral symmetry. So the scalar part of the model will be different from the pseudo-scalar part. This difference is not large, but it may bring meaningful difference when analyzing observables. So this is a comparison of the neutral pion mass calculated with this new model with the flavor coupling constants as a function of the magnetic field. And here there are several calculations with the standard non-Lagrangian model, with this corrected non-Lagrangian model by considering two different coupling constants, the scalar coupling constant and the pseudo-scalar coupling constants. And then there are some lattice calculation and two other usual parameterizations of the coupling constant dependence on the magnetic field. So we see here that this model calculated with the scalar coupling constant provides very nice results for weak magnetic field that agrees very well with lattice calculations. And then we can also do this comparison for the anti-up state that people do in lattice calculations. So there are here two lattice from two different groups. And then also we see the very good behavior at weak magnetic field for this up state. And for the down state too, the agreement is very good. So for low magnetic field, so if we look this as a whole, it looks like for weak magnetic fields, this flavor coupling constant, this behavior of the magnetic field induced coupling constants is nicely described by a simple model, kind of simple model, just like the non-Lagrangian, without taking into account gluon dynamics. So it suggests that at higher, stronger magnetic field, maybe gluon's degrees of freedom become more important. So for neutral kaon, the agreement is not so nice, so it agrees for weaker magnetic field, but still there is some agreement for very weak magnetic field as compared to the lattice results. So now I go to the main part of this work. I will discuss how we can obtain a constituent quark model from QCD-based effective action. So this, if we integrate out gluons, the leading term of this, the resulting effective action should be this one gluon exchange, where this gluon two-point function might be taken as an input for performing the calculations that I will show to you. So we can apply standard method as a first transformation to open up the flavor and Dirac channels to see what happens with mesons, and by applying again the one loop background field method, we can work out different quark and meson coupling constants. And that's the picture we obtain. We may have a quark, a background quark surrounded by a gluon cloud that will be also surrounded by a quark-anti-quark condensate. There is an interplay between these two corrections, but by working out the meson part sector of this model, of this theory, we have a pion cloud as obtained from chiral perturbation theory. They are the same terms, the same action, the same Lagrangian for the chiral perturbation theory. And then now we go to take into account in this calculation contributions of a weak magnetic field, so we can expand the quark propagator for weak magnetic field as compared to this constituent quark mass. So this is this propagator knows that quark mass is dressed by a gluon cloud and maybe a pion cloud, and then it provides some correction that has been worked out also in the literature. With this correction, we can perform nearly all analytical calculations for this model. And then we can interpret quark-anti-quark interactions now. They are surrounded by gluons. And then we have here the equivalent to two gluon exchange. But so these are the contributions I will show. But these two gluon, these are not the final rules from QCD. these Feynman rules here, I mean, this is just the diagrammatic interpretation of we obtain from the quark determinant in the presence of background quark currents. And then we have, if we look at the pion sector, pion interacts, we obtain pion as interacting to constituent quark currents. In all ways it's possible to couple by means of an axial coupling constant, and we have other mesons interacting with quark constituent quark currents, and these coupling constants become form factors that depend on temperature eventually and on magnetic field. So we have to fix the coupling constant at some cinematical point. I usually choose zero external momentum to fix this coupling constant. And usually it's enough to fix, I mean, to kind of implement a renormalization condition for one of these couplings. All the others become fixed. So this is being published in some works. And also, yes, this is being published in some works. And there is an unusual coupling that appears already at magnetic field and is corrected under weak magnetic field. Is we take a light vector meson like the rho or the omega or the phi. It may couples to the axial quark current. So this is, I cannot show here, but this is the axial quark current. This is the stress tensor of the isovector isovector meson. It is momentum dependent, and it has a form factor, a coupling constant, that is suppressed by this constituent quark mass, and it has this unusual structure. In fact, it corresponds to, I'll show in the next slide, to a sort of Esomino term as a whole. And this is for the rho vector meson. This is for the omega vector meson. And then we can include, to perform this calculation here with insertions of weak magnetic field in one of the quark, separately in one of the internal quark lines, and we have weak magnetic fields leading as linear in B. So these coupling constants are again form factors that depend on magnetic field, and they can be written as integrals in momentum. They are suppressed again by constituent quark mass squared, and they are quite highly momentum dependent. Of course, there is this anisotropy guided by this preferential direction of the magnetic field in the z direction. So we can invert the reasoning and take chiral partners of the vector meson. So we have axial mesons that are usually accepted to be quark anti-quark state, but some people argue they might be tetraquark states. In any case, this is a multiplet, a nonet of axial mesons that will couple to the vector quark current in this unusual way, with the same properties of the previous slide for the vector mesons. And then if you compare this vector meson coupling to the axial current to the pion axial coupling to the axial current, we have this sort of relation between the anomalous form factor and the axial pion form factor. They have basically the same structure, and the anomalous form factor is kind of suppressed by this factor. This factor emerges in the same way the Goldberger-Triemann relation appears in this formalism, in this way of calculated. But this is quite smaller. It would require a kind of high precision in determining this coupling that's not achieved nowadays. And then the magnetic field contribution, the leading magnetic field contribution, as compared to the value in the vacuum, is of the order of EB over m star square. This may be of the order of 0.01 GeV square for reasonable values of the quark constituent mass. So these form factors, they have the structure of a Vesumin-Witten term, so that we can place this form factor in a, we can face it as a hypersphere in the 5-dimensional, as a 5-dimensional closed surface, and then the resulting integral in momentum will be quantized. So this n lambda, this is a contribution for the action. It is, it should be quantized multiple of a integer multiple of a fixed quantity. And so if this probes the quark axial current, so the vector meson would provide some sort of topologically protected part of this axial current. And then I started to try to extract some more information, such as to apply some momentum profile for these quantities to try to understand which quantity is this one. So, but so far I didn't get a very well defined result. So this works both for zero, for the vacuum, but also for the magnet, in the presence of the magnetic field, for both equations. So besides these couplings, we find a lot of mixings between mesons that appear just as a function of the magnetic field, and that is difficult to understand how to probe, how to try to understand if they appear. If they appear, they might be some sort of hints that a magnetic field might happen in those situations, right? So here there is one of the most strangest. This is the vector meson. By applying the same procedure in the meson sector, this calculation becomes very akin to the Namuyo-Nalazino model calculations, but the form factors might be a little bit different. Here we can have some sort of gluon-cloud contributions depending on how we define this form factor. And then here there is a vector meson mixing to an axial meson. This is isotriplet. Both are isotriplet. Momentum conservation appears naturally as in that delta function. And they have this unusual coupling that's proportional to the magnetic field, linearly proportional to the magnetic field. No, wait, here. And then I also try to test effects of magnetic field in the vector meson dominance assumption and in vector meson mixings. So here there are these red characters stand for the photon stress tensor. And so here in the first term, these all resulting from the quark determinant. The first one would be a vector meson dominance type, because this is the neutral row coupling to the photon, and then the omega coupling to the photon. And below, we may have vector meson mixing because of the presence of the photon. So in a magnetic field, in a Schwinger gauge, we have here a magnetic field induced contribution for the vector meson mixing and also for the axial mesons mixing. And then I tried to test these couplings here by calculating the pion form factors, and that provides very small contributions that might be tested in high precision. Calculation, the fit is very good, but I didn't put a figure here, so I'll not show the result itself. And in this work also, of course, this is always the background field method. I try to implement it in a way that is gauge invariant. That's not always reached in the literature. Finally, I just mentioned some work we are doing with Marcelo and Cristian, is to calculate some unusual pion coupling to quark currents. So we take the leading terms with these weak magnetic field insertions, And then we are reaching some pion coupling to the vector quark current that appears in the vacuum. Our equations are almost nearly analytical, except for some final integrals in Feynman parameters. And so this pion coupling to a vector quark current may eventually provide us with a pion mixing to a vector meson So, and also another thing we started calculating is the an anomalous pion coupling to gluons, in which we have a similar diagram to this one. We can look at it in different ways. We have access to different processes, but all this is underway. So this I just let here this summary, and the fact now I'm looking for ways to test these coupling constants and form factors. Thank you for your attention.
Questions? No questions?
Okay, so I'm a bit confused about your treatment of the Weis-Minowitten action. So probably I didn't follow your argument, but usually the Weis-Minowitten is gauged to include the gauge field, but gauged with Weis-Minowitten is not gauge invariant enough, and so some subtraction, the term is added, etc., etc. That is a normal procedure. But in your case, so if this is a gauged Weis-Minowitten, or how did you include the magnetic field? That is not very clear to me.
No. There is no gauge field here, except if we interpret this vector meson stress tensor as in a chiral gauge way. So this would become a sort of chiral gauge stress tensor. So, but this is not a gauge theory, but the structure of the action of this Lagrangian is exactly the same as they interpret from the gauge theory.
Oh, I see. So I saw that you include the magnetic field, but
yes, I calculate that with a magnetic field in the presence of magnetic field. So. Yeah, I mean, I didn't write the corresponding equation in this case here, but I have exactly the same kind of integral in this case, but in the presence of an asymmetry. So these terms here also they have the same structure. These are the corrections for magnetic field corrections for those couplings, right?
Okay. So you treated the gauge potential as if it is the vector meson or something.
Yes.
Okay. Understand. Thank you.
If there are no more questions, let us thank Fabio again.
Has been a wonderful starting day for this conference. Thank you, Anna, first of all. Thank you, Giorgio, for inviting me to this conference. Chirality, vorticity, and magnetic fields in quantum matter. There is a lot of fabric to talk about regarding these subjects, and because of that, I am taking a slightly different point of view of what has been discussed during the day, because I'm going one step backwards and try to learn a little bit from topology, from the Dirac equation and supersymmetry, but we will see that eventually these things will connect because of the dynamics of charged particles in the presence of magnetic fields. So this is the work that we are doing with Eric, an undergrad student, and also with Juan Domingo, a dear friend and colleague, in which I have divided this talk in four parts. The first part is a historical part of how do we treat the dynamics of charged particles in magnetic fields. But one step backwards, I mean from classical mechanics to quantum mechanics and so on. And then I will describe one of the simplest but non-trivial models in which we can test the symmetries of induced by the magnetic field, which is the so-called Yakib-Revy model. And I will discuss briefly what this model is and what the connections are, not only with condensed matter and other fields of research, but also in the terms of quarks and other degrees of freedoms of relativistic matter. And I will discuss slightly what is the Dirac oscillator and how not to couple minimally the external magnetic fields into the Dirac equation, and then the analytic structure that this Dirac equation acquires from this non-minimal coupling that allows to see the topology and topological indexes emerging from these considerations. Not only from these considerations, but what are the implications of all that. And so I will go very, very slowly, recalling what is the dynamics of charged particles in magnetic fields. And this is basically because we need to remember at some point that this is foundational to understand, for instance, cyclotron motion and quantum spin dynamics, but also the strong connection with gauge invariance and the cornerstone of fundamental interactions. This way of treating or adding the dynamics in external magnetic fields would allow to understand the emergence of classical trajectories, quantum Hall effects, superconductivity, Landau levels, and all these ideas that we will be hearing about during this workshop and in this field as a whole. So basically, the idea is we start from the Lagrangian of a free particle, and then we recall what is the Lorentz force, this Lorentz force that couples a charged particle with external electric and magnetic fields through the velocity, but also recalling that the magnetic field can be written as the curl of a vector potential, and also this vector potential has this gauge invariance. Then the way of coupling this external field to the equations to the Lagrangian is precisely to this so-called minimal coupling that we all we have used so far in the discussions to include the effects of magnetic fields in the dynamics. But when we go to the quantum realm, we basically don't start from a Lagrangian, basically, but from a Hamiltonian of a free particle in quantum mechanics. And the way we do that is by coupling, by replacing the kinematical momentum with the canonical momentum in this form, such that the Schrödinger equation acquires now a more intricated form that includes or that possesses this gauge symmetry in which we can replace the electromagnetic potentials and the wave functions in such a way that the equations of motion remain invariant. So with these ingredients at hand, we see that we are already manipulating, choosing an appropriate way of solving these equations in order to make the problem more treatable. So what we do when we go from the non-relativistic to the relativistic quantum cases, what we basically like to do is to start the discussion in the Landau gauge, because equations of motion become more simpler. And if we go to the relativistic case, either when the Klein-Gordon or the Dirac equation are solved, we basically choose this gauge because we have a dimensional reduction that help us out to solve the problems. And basically the Hamiltonian in the former case is what I have shown before. And in the case of the Dirac Hamiltonian, it merely replaces the kinetic momentum operator, but we still have to include the dynamics due to the gamma matrices that come in here. The difference would be the scaling of the energy levels, which in the non-relativistic case are proportional to the synchrotron frequency, but in the relativistic case, we find this frequency under the square root sign. And therefore, we have two separate behaviors that can, at least for instance, when we go to a solid state systems, we can see whether the behavior of the charge carriers is one is related to a non-relativistic or to a relativistic description. And basically, the insight that we get from here is that in the non-relativistic case, we have a quantization in the perpendicular plane along the direction of the magnetic field we are considering, whereas in the case of the Dirac equation, we already have included the effects of spin and some other relativistic effects that will appear naturally in this framework. So with that at hand, one of the earlier attempts that it's a model, it's a very simple model, but it has some richness that because it is now again some attraction from the audience, because it's a model that serves to describe a modern system like topological insulator materials. But it's not the only way. It also has some connections with models that help to describe, for instance, one-dimensional systems in condensed matter, but also topoelectrical circuits, that is a macroscopic stuff made of resistance, capacitors, inductors, that one can check in the laboratory. And the good idea, or the main idea of this Jacquier-Brevy model, is a fermion field which is interacting with a spatially varying scalar field which has no dynamics. The trick of this field is that it changes the sign on the left-hand side and on the right-hand side, and we can, for instance, attach it to a mass that won't have the same sign in either side of the x-axis. It is negative on one side, it is positive on the other side. The constants could be different in principle. And this model, this Dirac equation that is the Dirac Hamiltonian that appears at the bottom of this slide, has a solution zero modes. That is, it has very intriguing, very interesting solutions. And perhaps the interesting part is it's a topological system, because we can describe these zero modes as solitons or domain walls. And this model was presented in 1976, and it shows charge fractionalization and other features that were discussed even before we were familiar with the quantum Hall effect and other problems in classical problems in condensed matter physics. So basically, these zero modes are topologically protected at domain walls, and as I mentioned before, they have the shape of a kink. That is where in the interfaces of different materials, these kind of solutions naturally appear and are relevant to, for instance, unveil the electric properties of these kind of systems. So this idea, again, of fractionalization of charges was presented even before the fractional quantum Hall effect was discussed or discovered later in the 80s. So these gapless modes that appear at the interfaces are very interesting, because they would help to understand what is, for instance, the nature of some one-dimensional topological insulators. These kind of objects are conductors in the edges of the material, of the strip, of the wire, that if you wish, that is composed the material, but in the bulk that is in between, the material is completely isolated. And this is why we become interested in this kind of models. For instance, when we go to discuss chains of polyacetylene models, the discrete version of the so-called Jacquier-Brevy model would be the SSH model, which appears somewhere in there, where we have a chain of atoms, but the atoms are changing species, A, B, A, B, A, B, and so on. So the hopping parameters also change between the two neighboring atoms. And by neglecting, for instance, a first approximation and keeping only the lowest Landau levels, it turns out that depending whether T1 or T2, the two hopping parameters, one is larger than the other, the model could exhibit a non-trivial topological phase or not. And this is very interesting because when we go to the tie-binding description of this model, we can see that the natural emergence of edge states that could somehow help us visualize the topological nature of the Yakiev-Revy mode. And these edge states will correspond naturally to the zero energy states in the continuous model. And what we have found very interesting is that in turn these tie-binding models can be mapped to a classical model in which every atom can be replaced by an array of capacitors and inductors that you can build in the laboratory. And then the full change can be described in terms of this change of electronic circuits in which you can switch at will the capacitances and inductances of your circuit, and you can test actually on macroscopic grounds what would be the behavior of a topological system such like that. And this topological system that appears in here is such that, for instance, the voltage would have a localized behavior at the edges of the full change of components, and this will be mapped directly to the wave function of the edge states that are developed in the Yakiev-Revy model or in the SSH model. These topological phases can be, again, accessed to on classical electric circuits. And so the domain walls that appear in here would correspond to the impedance mismatches in the measurements of these circuits. And the edge modes will manifest as localized resonances in circuit voltage or current distributions. And this is very interesting because we get to see topology in the laboratory. Over there is a plot that we have calculated and actually published, where we can see we have made sure to select the mapping of what would be the hopping parameters to the values of the capacitors, the capacitances of these elements, these circuit elements. And what we are seeing is that we are picking the system with a sinusoidal signal, and we get to see the development of a resonance at some particular points, and these resonances actually correspond to impedance measurements, and we see that this can only appear in there if we select the elements such that we are in the topologically non-trivial phase. If we just move one side the chain, we immediately see that this resonance vanishes and all. And on the lower panels, we see the localization of the voltage at the different nodes of our circuit, and that is mapped again to the emergence of the localized edge state in the tie-binding model that we can see in these classical systems. Now, for instance, we have a comparison of what happens with the Yakiev-Revy model and some electrostatical systems that appear in here, and we see that there is a one-to-one correspondence between what are the features of the Yakiev-Revy model and the electrostatic system that appear in here. So we have the means to check how the emergence of topology can be checked in this kind of systems, but also what is very intriguing is that the equations of motions are very similar in both the cases, and they are reflected to, or they are directed to the model, the equations of motion of the Yakiev-Revy model. And in order to show that, what I have to resort to is to the Dirac-Moshinsky and Szczepaniak oscillator, which is a model of a Dirac equation in which an external field is coupled non-minimally in the effective equation. Basically, the Dirac oscillator that appears in here is what when we have the usual harmonic oscillator potential coupled with in this case, the Dirac Hamiltonian that comes in here. One can check that the energy levels in this case can be obtained directly from what we know from non-relativistic quantum mechanics, and so this Dirac oscillator has been discussed from the 80s precisely by Dirac, Moshinsky, and Szczepaniak, a Mexican physicist, in which they use the following trick to incorporate the effects of the magnetic fields. Rather than using the minimal prescription, what they do is replace the momentum operator in terms of a gamma 5 and this linear displacement of the position, such that the Dirac Hamiltonian now has the following form. They have gone and described what is the spectrum of this Dirac oscillator, and what we are going to do next is trying to see what happens with this model. But let's go to the simpler scenario where we have only one spatial dimension in this case. So the coupling, the non-minimal coupling that appears in this model is due to a spin-orbit coupling, which in the field of topological insulator plays a leading role that we want to understand. And so there is naturally a modification of the energy spectrum, because somehow we have a coupling between position and spin degrees of freedom. And of course, we want to see whether there is a symmetry breaking that could take place in here, or a system like graphene or other lower dimensional topological systems. What would be the effect of this coupling with a position-dependent mass? So what the question naturally arises because when we were discussing with some colleagues from the solid-state community, they say, well, you have a Dirac equation with an effective mass, very good, but how do you get to see the topology of this model in an actual sample, in actual calculations in this case? And the emergence that we have found is through the natural supersymmetric structure that we can find in the Dirac equation under these conditions. In quantum mechanics, we have a supersymmetric framework where we can factorize a Hamiltonian very similarly to what we do with a harmonic oscillator. And we see that this Hamiltonian actually has a cosine Hamiltonian in which the order of these two operators is interchanged. And what happens is that the spectra of these two Hamiltonians are very closely related. One could imagine that there is a one-to-one correspondence between every energy level, but actually it could be, and this is basically the case for us, in which there is an additional state that comes only in one portion of the Hamiltonian, but not in the other. That means, for some historical reasons, this is called the bosonic Hamiltonian. This is the fermionic one, and we get to see that the two Hamiltonians have a very similar spectra, except that for the ground state. For in this case, it's a zero mode that appears in here. And this difference makes the appearance of a first-order supersymmetry, and this scenario is the so-called unbroken SUSY that Witten has discussed in his original paper on supersymmetry, where he defined an index, which we now call the Witten index, in which this index is an integer 1 if the number of fermionic states is larger by 1 than the number of bosonic states. And in this case, we are seeing, or we say, that we are in a topologically non-trivial phase of this interwinding of the two Hamiltonians. And we will see that we can connect the behavior of the topology of the Yakib-Revy model Yes, to this mathematical structure of the Dirac equation. And in this work, Gonzalez and other collaborators wanted to explore what could happen. Imagine the following example. You have an infinitely charged sheet of some material, and it separates two dielectric materials with different dielectric constant in each side. And when one tries to solve the corresponding Maxwell equations, one ends up mapping these Maxwell equations to a one-dimensional Dirac-Moszynski-Szczepaniak oscillator in this form, where here is the electric field in either side of the interface. And this Hamiltonian has the trick that it can be written in terms of a spinor wave function, and every component of this spinor satisfy a Schrödinger equation with a supersymmetric structure. That means that we have H1 and H2 with two different potentials that appear in here, and these two potentials are the super partner potentials in this case. This is where Gonzalez et al. Have discussed in this, and this is the specific form of the two potentials. So they find that the equations of motion can be solved for a zero mode, and the corresponding solutions are one with a C minus and the other with a C plus, and this phase that appears in here, which is basically the integral of this quantity that appears in here. The thing is that the two states are not normalizable simultaneously, so one has to choose one or the other to normalize at a time. And because of that, the spectra differ by a zero mode. And this is important because we already see that the topological nature that comes in here. So basically, this is what they describe as the soliton, the Yakib-Revis soliton, in terms of this electrostatic potential that comes in here, because it's basically a textbook exercise to solve this problem. Now, what we want to do is do a similar thing and make a replacement on the momentum operator with a generalized form of this coupling here, and we will refer to this function as the superpotential. And when we try to solve the corresponding equations of motions, we end up with a pair of Schrödinger-like Hamiltonians with this generalized potential that appear in here. And yes, you have already guessed that the difference between the two of them is that one of them has an additional state, an additional state that we can solve for the zero modes. The zero modes will be then found in terms of this superpotential, but we cannot normalize both of them simultaneously, so we have to pick one, and because of that, we have an additional zero mode in a spectrum. For instance, here we have selected H0, and so the Witten index for this problem is preserved, and we have unbroken supersymmetry. And this is very relevant because every other topological index that we could associate in this model can be written in terms of this Witten index. For instance, Sachs phases, winding numbers, and so on, that you can describe. Actually, the appearance of this resonance in the impedance is in accordance with this Witten index. We haven't been so far discuss what is the name of this resonance in literature. So it could be, but somehow on physical grounds, it is directly related to this Witten index of the problem that is at hand. So here, the work of the student actually is, well, try to see which kind of solutions you get here from different superpotentials that you can define, and see whether these are normalizable or not, and see all these exercises that we could have. What are the solitons for different profiles of this superpotential, and so on. And we need to give such a superpotential a spin orbit interpretation. This is work in progress, and the connection with topological phases, for instance, in SSH model or topological circuits, and so on. This is something we are working on, but we already see that we have all the clues together. We only have to put the pieces together to find the puzzle that it comes in here. So with that in hand, I thank all for your attention, and thank you, Anna, again.
Questions? No questions? You do.
It's on. This is quantum mechanics, right?
Of course.
And in relativistic quantum mechanics, you have things like the Klein paradox and stuff like that. You do not have a unitary representation of the Hilbert space,
okay.
right? You have the Fock space.
Of course, yes. For condensed matter systems, you need to be a little bit careful because you still can describe some of these materials within the first quantization. You don't need to go to a second quantization in order to do that. But you are right. If we want to translate whatever we have done here to the next level, we have to be very careful with the Fock, with the Fock space in this case. Nevertheless, just one thing. For instance, we have been hearing about the propagators, the Schwinger propagators. There will be at some point the discussion of the Ritus propagator. All of these guys are nothing but the supersymmetric quantum mechanics equations of motion eventually.
More questions? Yep.
First, I would like to thank for the presentation. This is a naive question that I was thinking about. You comment about the topoelectric systems.
Yes.
Topoelectric circuits, I guess.
Yes.
Exist some topomagnetic circuits? I don't know. It's a naive question.
Oh, that's a good question. I guess they are called topoelectric because it's closely related to electronics. And this is because we have these guys only capacitors and inductors involved. I don't know whether there would be a magnetic version of these objects in here. That's something that it's worth just taking a look at the literature.
Thank you, Alfredo. All those systems are considered infinite?
No, actually, what we have described in these plots is a finite system, and that's, because it is finite, you get to see the localization at the edges of the system.
So the edges are fixed.
Yes.
Okay.
So thank you for a nice talk. Just a brief comment. I mean, anecdotically, every electric circuit is a topological object because you have two topological invariants, which is the net capacity
Yeah, you are right. Yeah.
and the net resistivity. And it doesn't matter how you deform the circuit, you still get these two invariants.
Okay, very good. Yeah.
So let's thank Alfredo again. Okay, so now we have a discussion session. So everything you couldn't ask during the day.